Welcome to the Mipar tutorial on local measurements. This tutorial will focus on a few different applications of the local measure tool in the image processor. So let's go ahead and get started. We will start with a particle image, in this case gamma prime in a gamma matrix. In nickel-based superalloy we have the larger secondary particles and the smaller tertiary particles as they're known. And let's load in a recipe that we have made to detect the different particle populations. We've got the secondary in green and the tertiary in red. And a quite powerful and unique tool in Mipar is the ability to, of course, not only globally measure a value like area fraction, not only feature by feature measure things like diameter, but to map out variations in any of those measurements. And that's what we're going to show today. So let's suppose that we wanted to measure the local area fraction variation just across this image. We can either show the image that we want to measure and click local measure, and that'll take us right into the local measure tool. Or if we were looking in layers mode and we click local measure, it will ask which layer do we want to take a look at. So in this tool now we have a few different measurements that we can directly perform, but you'll see we can perform many others through an additional workflow. Area fraction is probably the most common local measurement. This is going to generate a measurement per pixel by sliding a window through the image. And then we'll also look at local thickness, which visualizes the thickness variation across a set of features. These other two are useful for looking at quantifying local orientation and anisotropy differences, anisotropy being a measure of local homogeneity or directionality. And the nearest distance can be useful when looking at plotting pixel by pixel the distance from something relative to something else, where an asterisk here indicates that you need to have a companion image set, a binary companion image set as the something to measure from. But we're going to look at area fraction and thickness in this tutorial. With area fraction as the default measurement, we then have a set of parameters to adjust. The window size is simply the amount of the size of the window to consider around each pixel. And sliding versus blocks indicates whether we slide the window along all pixels, so if every pixel has its local window considered, or with blocks, let's say we had 35 blocks, as a window size of 35 under the blocks method, we can then set the step size, which basically for a sliding method, the step size is 1. Blocks allows you to set a different step size so that you could conceivably have a box of 35 pixels and then step it to the right by 5 and take another box, and then all of the pixels within each block get you would not be measuring directly a value for pixels in between pixels 2 and 4 in that example. The measurement would be made around the first pixel and then around the 5th pixel, and the ones in between would be interpolated. This can be useful for images that have periodic structures where sliding across every single pixel can produce some artifacts in the measurement. We won't really demonstrate this today, but it is there as a tool to help get over some periodic structures that can appear. Sliding is the most commonly used. Checking the window size, so checking show window size just lets you visualize a example of the size of the window that is going to be slid across the entire image, starting in the top left. The box gets centered around every pixel. So the first box will actually be centered around the pixel in the upper corner, and of course Mipar is smart enough to realize that we only are going to be able to use 1/4 of the box in that corner. until the box fully moves into the image frame. So let's say that we wanted to use a box size something like 240. This is going to measure the local area fraction about each pixel in an area like this about each pixel. So we hit generate and we now get pixel by pixel for each pixel in the image the local area fraction. And if, as with the color by measurements tutorial, if we just click a cell in the column of interest, we now have a visualization of the area fraction of the features transparently overlaid on the reference image. And let's turn that off so we can get a better view. And of course we have our color scale over here. You also get a histogram of all the measurements that you've created. You can adjust the bin size like before, and you get min, max, standard deviation, and mean statistics of this histogram. Right click on them to copy the entire set to the clipboard for pasting. We have point probe and line profiling tools to investigate the variations quantitatively. And you, of course, may export the entire table that you see here, or even an average of the map values, whatever is mapped, that fall inside of the features that generated the map in the first place. So it's perhaps more useful with something like thickness, where if you have the local thickness of every feature plotted, you can then export a spreadsheet that has the average thickness per feature, which can then be imported into the color by measure tool to display a single average thickness value per feature. Next, I'm going to show how you can really take any measurement that you can make on a per feature basis from the color by measure tool and turn it into a continuous map of that same measurement. So let's close out of this. We'll go into our color by measure tool using the secondary precipitates, and here we can generate the measurements that we wish to ultimately plot pixel by pixel. Let's choose equivalent diameter, which is the diameter of every particle if it was a circle of the same area, a common scalar metric of size. And here we have that measurement made for every feature in pixels. Because we have not calibrated the magnification, do feel free to check out that tutorial. And as we saw in that tutorial, simply clicking a cell in this column takes that column of measurements and color codes them accordingly. So now every feature is colored according to its equivalent diameter or size. And we also get a histogram of those same measurements. Now we can take from the export option the local means, enter a window size. We can use 241 like before. We can show the window size as we did in the local measure tool. And if we hit export now, we're going to generate for each pixel, the average equivalent diameter, or the average whatever is selected here, in a window size about 241 pixels for each pixel. Those data will then directly import into the local measurements tool, and now for each pixel we have the mean equivalent diameter. Select this column to visualize that data. So now you can visualize some trends that may not have been quite as obvious before. We see areas where locally the average particle size varies quite a bit in some cases. And of course we have a histogram of that data. All of the same exploratory tools are available as they were before. We can really take any measure that you can make per feature and map it continuously across the image. Next, I will show exploring a different set of features to measure their local thickness using the local thickness measurement of the local measure tool. Let's close out of these windows and open an image with some acicular features where we might want to visualize their local thickness. We'll run a recipe for their detection. And now let's take the alpha phase, which is this needle-shaped or plate-like feature. We'll show that, and we'll go directly into the local measure tool. Let's choose thickness from the drop-down, and you now see this checkbox changes to show skeleton. What's going to happen is, well, what has already happened is the skeleton of all of these features has been calculated, and we can show that here. There are two methods for calculating the skeleton, classic and advanced. Well, there are four, but only two are really applicable to this problem. Classic uses a more traditional skeletonization. Advanced uses a thinning algorithm, which cuts down usually on the number of small branches. There might be some cases where you need to use a trim threshold to reduce branches or eliminate branches that are under a certain size. Say something like, well, that's too high, but something down there, maybe 50 pixels for a threshold. We'll start to get rid of small spurs like this that we had with a 0 trim threshold. It can also get rid of small line segments, though, that are seen as branches in between two spokes. So we might want to take this down to maybe 20. And what's going to happen is now with this skeleton set, when you click generate, you're going to measure the thickness value of the feature at each point along this red skeleton. We don't want to bias our results by making thickness measurements from every pixel in every feature, because obviously in thicker regions we have more pixels. If we measured the thickness for each of these pixels, it's then going to look like, on average, our features are thicker than they are, because the thicker features are going to contribute more pixels to the histogram. So we actually only take the measurements along the red line, but then we still smear out that color, for lack of a better term, to the rest of the feature, so that we see a nice continuous map simply for visualization. But what will appear in the table and what will appear in the histogram all belongs to the pixels along the red lines. So we hit generate, and then we make those values, we make those measurements. You see we don't have all pixel ID numbers listed on the left, because again, these are only pixel IDs that came from the locations under the red lines. Click in the column to set the measurements, and let's hide the skeleton, and you see now that we have local thickness of these features visualized for every pixel that belongs to the features. And we have a histogram now as well of, and a mean and min and max standard deviation of the thickness measurements. So that is local measurements. Please let us know how you are using the tool or any suggestions for improvements that you have. Do feel free to contact us with any assistance required, and don't hesitate to send over those images for some custom recipes. Also, feel free to book training anytime at mipar.us/training. Thank you very much for your attention, and we'll see you in the next one.